In this video, we will look at common questions that involve geometrical relationships between a point and a line. Given a point and a line, some of the more common relationships that we can find are, number one, the foot of perpendicular from a point to the line. So from this point, I can drop a line down towards the line, which is perpendicular. And at the point at which they intersect, this is the foot of perpendicular, which we usually denote using the point F. Next, I can also find out the shortest distance between the point and the line, which is coincidentally the perpendicular distance between the point and the line, or the distance from our original point to the foot of perpendicular. Thirdly, we can also reflect the original point about the line to get a point of reflection about the line. To find the foot of perpendicular, we will illustrate using this point A and this line L. Firstly, we let the foot of perpendicular be a point F, and this point F has position vector that follows the equation of the line. So we have OF equals to lambda, 1 plus 2 lambda, lambda. Next, we will form the vector AF. AF is simply OF minus OA, which is equals to lambda minus 5, 2 lambda minus 1, lambda minus 5. And the reason for finding AF is because we know that AF is perpendicular to the line, and therefore we can make use of the dot product property, where dot product of the two perpendicular vectors equals to 0. So now I can say that lambda minus 5, 2 lambda minus 1, lambda minus 5, dot with 1, 2, 1, it must be equals to 0. Finally, if we solve this dot product equation, so we get lambda minus 5 plus 4 lambda minus 2 plus lambda minus 5 equals to 0, we will be able to get a certain value of lambda, which is equals to 2. And this value of 2, when we substitute it into our equation for OF, that will give us the position vector of the foot of perpendicular. So in this case, we can say that OF must be equals to 2, 5, 2. In example 1a, we have the point 0, 3, negative 16, and the line r equals to 1, 3, 2 plus lambda 4, 0, negative 3. So this point A, 0, 3, negative 16, and this line r equals to 1, 3, 2 plus lambda 4, 0, minus 3. And I'm interested to find out the foot of perpendicular F over here. Therefore, I can just apply the steps that we have learned earlier. Number one, I will find what is OF in terms of lambda. It will be 1 plus 4 lambda, 3, 2 minus 3 lambda. Next, I will find out vector AF, which is OF minus OA, and that gives me 1 plus 4 lambda, 0, 18 minus 3 lambda. And next, I know that AF is perpendicular to the line, which means AF dot with 4, 0 minus 3, it must be equal to 0. So I have 1 plus 4 lambda, 0, 18 minus 3 lambda, dot with 4, 0 minus 3 equals to 0. Now I simply have to expand this to get 4 plus 16 lambda minus 54 plus 9 lambda equals to 0. And solving this equation gives me lambda equals to 2. Therefore, I can substitute this value of lambda equals to 2 into my OF to get 9, 3, negative 4, which is the position vector of the foot of perpendicular. Next, we look at how to find the shortest distance between a point and a line. This is also the perpendicular distance between the point and the line, and thus it is the length of the vector AF. Therefore, if we have already found the foot of perpendicular OF, we can proceed to find AF. So from earlier, we know that OF was found to be 252. And that means we can find what is vector AF very easily. It will give us -3, 3, -3. And once we find vector AF, the modulus of AF will give us the shortest distance, which means shortest distance must be equals to mod AF, which is equals to mod of -3, 3, 3, which is equals to square root of 27 units. Example 1b is a continuation of example 1a. In example 1a, we have found the position of the foot of perpendicular to be 9, 3, -4. So we know that OF is equals to 9, 3, -4. And what we are interested to find now is the length of vector AF. So we have to find what is vector AF. It will be 9, 3, -4 minus 0, 3, -16, which gives us 9, 0, 12. And therefore, the shortest distance will be equals to mod AF, which is equals to mod of 9, 0, 12. And mod of 9, 0, 12 is the same as 3 times of mod of 3, 0, 4, which gives me 15 units. Sometimes the question doesn't require us to find the foot of perpendicular before finding the shortest distance. In cases like this, of course, we can continue to find the foot of perpendicular and use it to find the shortest distance. But this is a very long method, and given the time constraints of the exam, it is advisable for us to explore a shorter method, which I will explain now using the same point and the same line as earlier. First, we will find a random point on the line L. For convenience, I will usually choose the fixed point given in the equation of the line, which is 0, 1, 0. So I can say that OB has position vector of 0, 1, 0. Next, I will form the vector AB or vector BA depending on your preference. In this case, I would like to form vector BA, which is equals to 5, 1, 5. Finally, notice that the shortest distance AF is simply the length of rejection of the vector AB onto the line L. Therefore, we can use the formula for the length of rejection, which is modulus of AB cross D cap, to find the shortest distance. So therefore, shortest distance will be equals to mod of AB or BA, so it is 5, 1, 5, cross with 1, 2, 1, divided by mod of 1, 2, 1, because it is D cap and not just a D. Now if we simplify this, I will get mod of 9, 0, -9, divided by mod of 1, 2, 1. And if we evaluate these two modulus, we will end up with the same answer as earlier, which is square root 27 units. Example 2 uses the same point and same line as example 1, so as to illustrate to you that both methods will actually give the same answer. So now I have the line L and the point A. So the first step is for me to find a point B. And I'm going to let point B be 1, 3, 2. And therefore, I can form the vector AB after this. Vector AB will be equals to 1, 0, 18. And thereafter, I can perform my cross product using the length of rejection formula. So shortest distance equals to mod of 1, 0, 18 cross product with 4, 0, minus 3 divided by mod of 4, 0, minus 3. And let's simplify this cross product over here. This will give me mod of 0, 75, 0 divided by mod of negative 4, 0, negative 3, which becomes 75 divided by 5, and this gives me 15 units, which is the same answer as in example 1. Given a point and a line, we can also reflect the point about the line to find the point of reflection. To find the point of reflection requires quite a number of steps. Firstly, we will need to find the foot of perpendicular from A to the line, which we have found earlier to be OF equals to 252. Now, assuming that we have found the foot of perpendicular, the next thing is to realize that the foot of perpendicular actually bisects the point A and its reflection. So if I draw a straight line to join A to F to A prime, they actually fall on a straight line, and F is exactly in the middle, and therefore I can make use of ratio theorem to write down this equation over here. Thereafter, we can rearrange this equation to make OA prime the subject, and thus find out the position vector of the point of reflection, which is A prime. So based on this, I will have OA prime equals to 2 times of 252 minus away 525. And this therefore gives me minus 1, 8, minus 1 as the point of reflection. In example 3, now we are asked to find the point of reflection of point A about the line L, both of which are the same as in example 2. Therefore, I know that I have the line L, the point A, which is at 0, 3, minus 16, and I'm interested to find out the point A prime. One thing I need to know is what is the foot of perpendicular F. And from earlier, we have found that F has coordinates of 9, 3, negative 4. And therefore, we can say that OF equals to 9, 3, negative 4. And since OF is equals to OA plus OA prime over 2, this tells us that OA prime is going to be equals to 2OF minus OA, and therefore this becomes 2 times of 9, 3, negative 4 minus 0, 3, minus 16, and on evaluating this will give us 18, 3, 8 as the point of reflection of point A.